Hello students, in today's lecture we are going to learn about thermodynamics NCERT section 11.4 to 11.5. This is disclaimer, learning objectives. By the end of this lecture you will able to understand the concept of heat, internal energy and work. Then apply the first law of thermodynamics to solve basic thermodynamic problems. Differentiate between the various forms of energy transfer in thermodynamic processes. So, according to uh, NCERT, in today's lecture, we will cover 11.4 heat, energy, internal energy, and work. Then 11.5 first law of thermodynamics. All right. So, heat, internal energy, and work. Here, we will understanding heat, state functions, and path functions in thermodynamics. Now, let's talk about heat. So, basically, heat is the energy transferred between a system and its surroundings due to a temperature differences between two bodies. Heat is a form of energy, so it is a scalar quantity. It means it has a only magnitude. There is a no direction. And the dimensional formula of the heat is ml square T raised to the power minus 2. SI unit joule or calories. Joule denoted by capital J, whereas calorie denoted by CAL. And there is a relation between joule and calorie. So we can say 1 calorie is equal to 4.2 joules and 1 joule is equal to 1 by 4.2 calorie. Yes or no? So here we conclude that heat is a form of energy that is flow from one body to another body due to temperature difference, or here heat flow from higher temperature to lower temperature. Now, heat is a path dependent quantity. This is very important concept. We know heat is a scalar quantity. So here the path dependent quantity means we can say amount of heat transferred during a process depends on specific path taken by the system to go from initial state to its final state. It means here we have a two path, path A and path B. All right. The initial state is 1 and final state is 2. Now, uh, if the process are going on going on by path A and the second process by a path B, in both cases, uh, heat will be different. All right, because heat is a path dependent. It depends on path. It does not depends on initial and final position. So here we can say heat is a path function. All right, heat is a path function. So along path A, along path B, in both cases, the amount of heat will be different. All right. So reason is what? Reason is heat is a path dependent quantity which depends on specific path. Now, state functions. Here we have two functions. First, path functions. Second, state functions, or we can say point functions. Point function means uh, initial point and final point. So basically, state functions are the values which depend only on initial and final states of the system. Initial state and final state, not on the path taken to reach those states. Their change between two states is independent of the process. Example: temperature, pressure, volume, internal energy, enthalpy, and entropy. So these are the examples of state functions which depends on initial point and final point, or we can say initial state and final state of a system. Now think about it. If the initial state and final state both will be same, then what will be the their specific value? So in that case, their specific value will be 0, because here the initial and final states are same. So in upcoming lectures, we will learn about uh, learn more about state functions like internal energy, enthalpy, and entropy. All right. So in simply we can say state functions is a path independent functions which depends on only on initial and final point, not on the path taken by the processes. So we can differentiate between state functions and path functions. So we can say in path functions, uh, the values, or we can say macroscopic variables, depends on initial macroscopic variables depends on no it independent of path. It depends on initial and final position. But in state functions, it depends on initial and final position. All right. Now, path functions. Path functions are the values which depend on the specific path or processes taken between two states. Their values are process dependent. Means it depends on process. They don't depend on initial and final point. It depends on path. Process first, process second, like this. Examples: heat and work. So these are the examples of path functions. All right. Heat transfer can occur in different ways. So first, for change in state. Here change in state means we know three state: solid state, liquid state, and gaseous state. So for change in state, solid to liquid, liquid to gas, and vice versa, gas to liquid and liquid to solid, like this. So for material undergoing phase transition, or we can say phase change at constant temperature, in that case the heat transfer delta Q is equal to ml. All right. The important point here is the at constant temperature, where Q is equal to heat energy measured in joules and symbol is capital J. All right. M is the mass of substance measured in kilograms and symbol is small kg. L is the latent heat of fusion or latent heat of vaporization, symbol joule per kg. All right. Now, second process for change in temperature. So for material undergoing temperature change without phase transition, in that case, delta Q is equal to mc delta T. Now, what is the meaning of the symbol? So where delta Q is the heat transferred, measured in joules, and symbol is capital J. M is the mass measured in kilogram, symbol is small kg. Small c, specific heat capacity, unit is joule per kg per Kelvin. Alright. Delta T, change in temperature, symbol is capital K. So this is the second way of heat transfer. Third is for constant volume. It means when volume remains constant during heat transfer. So in that case, delta Q is equal to mu Cv delta T. Alright, where delta Q is equal to heat transferred and measured in joules, unit capital J. Mu is the number of moles and symbol is mu, measured in mol. Cv, specific heat capacity at constant volume, unit joule per mole per Kelvin. Delta T, change in temperature, measured in Kelvin, symbol is capital K. Similarly, the another way of heat transfer is for constant pressure. So when pressure remains constant during heat transfer, so delta Qp is equal to mu Cp delta T, where delta Qp is equal to heat transferred measured in joules and symbol is capital J. Mu is the number of moles, symbol mu, and measured in mol. Cp, specific heat capacity at constant pressure, unit is joule per mole per Kelvin. Delta T, change in temperature measured in Kelvin, unit is capital K. Alright, so these are the heat transfer ways and their formulas. Internal energy. So as the name is internal energy, so internal energy of a system is the energy due to molecular motion and molecular configuration. So there is a two type of energy present. First, due to molecular motion. Second, due to molecular configuration. And the sum of energy due to the molecular motion and due to the molecular configuration is called internal energy. Alright. So it is a macroscopic variable of the system. Internal energy of a system is denoted by U, capital U. Internal energy, or we can say energy, energy due to molecular motion. Molecules move randomly in a closed container. So we can say the energy due to molecular motion is called internal kinetic energy, UK. Whereas the energy due to molecular configuration is called internal potential energy. So here we have a two energy: internal kinetic energy due to molecular motion and internal potential energy due to molecular configuration. So the sum of internal kinetic energy UK and internal potential energy UP is equal to internal energy. All right, mathematically we can say total internal energy U is equal to UK plus UP. Internal kinetic energy UK plus internal uh, potential energy UP. All right, internal energy. Now, change in internal energy does not depend on path. It means it is a state functions. You know, state functions are the functions which does not depend on path. It depends only on the initial and final position of the process. If the initial state I and final state F, if both will be same, so in that case, the change in internal energy is equal to 0. But if initial state and final state are different, in that case, the change in internal energy is non-zero. So here, in simply, we can say internal energy depends on initial and final position of the states. So delta U is the change in internal energy is equal to UF minus UI. Here, UF is the final internal energy, whereas UI is the initial internal energy. Change in internal energy in a cyclic process is always 0. Now here question arises, why? Why change in internal energy in a cyclic process is always 0? The answer is very simple. Think about it. So we know change internal energy is a path independent. It depends on initial and final positions of the states. So look at here figure. There is a two path. First, this one, and second, towards up. So if the initial state I and final state F, both will be same. So in that case, the change in internal energy is equal to 0 because it is a path independent. It depends on initial and final position. Here, initial and final position are same. So we can say the change in internal energy in a cyclic process is 0 because in this process, initial and final position is same. All right. If we talk about the if the initial and final positions are different, in that case, the internal energy is non-zero. All right. So this is very important concept for solving the numerical problems. So remember this. Now suppose we have a container. So in that container, holding the gas molecules, gas particles, and they are at rest. If they are at rest, so their initial velocity, or we can say their velocity, should be 0. Yes or no? So V equal to 0. Now, what about the internal energy? So the particles having at rest position. So the energy due to motion of the molecule plus due to molecular configuration. When we add the energy due to molecular motion plus energy due to molecular configuration is the internal energy. So here the gas particles having at rest. So their internal kinetic energy should be 0, but they possesses internal potential energy due to their molecular configuration. All right. So all molecules motion related energies are summed to determine U. If we add the energy due to the molecular configuration and due to the molecular motion, so uh, and that is the internal energy here. All right. When the container with the gas is moving as a whole with a certain velocity. So look at figure 11.3 B. So here the container with gas is moving as a whole system with some certain velocity. So do not include the kinetic energy of the entire box in U, because the energy we consider only for molecular configuration and molecular motion, uh, uh, not for not we consider the kinetic energy of the entire box. So here we only consider for molecular configuration and molecular motion. Internal energy U focuses on the energy related to internal molecular dynamics, not overall the motion of the container. So from this line, it is clear that the internal energy, it depends on the molecular configuration and molecular motion. If the molecular configuration and molecular motion is changed, so their internal energy will also change. Or here, uh, we can say the internal energy depends on temperature. More about this concept we will learn in next. All right. Understanding how internal energy changes through heat and work. So first here we consider a gas uh, contained in a cylinder. Look at figure 11.4a. So a cylinder having gas particles with a movable piston. This piston is a movable. This system's internal energy can be changed in two ways. First method is heat transfer. Second method is work done. So we will uh, learn each one by one. So understanding here how internal energy changes through heat and work. So first method, heat transfer. The transfer of heat from one body to two body due to the temperature difference. So placed cylinder in contact with a hotter body. So this one is the hotter body and the cylinder is placed on that. So temperature differences causes, and due to this temperature difference the energy will flow from one body to another body, or we can say hotter body to cooler body, colder body. All right. So due to temperature difference, energy flow from hotter body to colder body, and this transfer of heat increases the internal energy of the gas. All right. So from this line, it is clear that internal energy depends on temperature. Yes or no? Because when we provided the heat of the gas particle, the temperature will be increased. If the temperature increase, so there will be create a temperature difference. If the temperature difference is create, so the heat transfer will there is a flow of heat transfer from hotter body to colder body, and due to this, the internal energy of the gas increases. All right. Now the second method is work done. So now push the piston down, doing work on the system because the direction is vertically downward. So the mechanical work increases the internal energy of the gas. So no temperature difference or heat transfer needed. All right. So work is the energy transfer about by means uh, moving the piston by raising the lowering some weight connected to it. So do not involve such as temperature difference. Now, mathematically, work done. Delta W is equal to integration dW, and we know the dW is the PdV. Lower limit Vi, initial volume Vi, and final volume Vf. When we give the temperature of the cylindrical box or cylindrical container, their volume will increase. So initial volume changes after some time when we heated the cylinder. So this is the low. This indicates the initial volume before heating and final volume after heating. So delta W is equal to integration Vi to Vf PdV. Here, when we integrate it, it will be P into final volume minus initial volume. Delta W is positive. It means the work done is equal to positive. It means final volume is greater than initial volume. So here, system expands. If the system expands, the work done is positive. Delta W is equal to negative if Wf is less than Wi. System contracts. Alright. So there the work done is negative. First law of thermodynamics. And this is very important concept. So statement, the amount of heat supplied to a system delta Q is equal to sum of increase in its internal energy delta U and the work done by the system delta W. Mathematical formation, delta Q is equal to delta U plus delta W. So listen carefully. When we provided, when we supplied, when we supplied heat to a system delta Q, right? So system will use that heat first to increase the internal energy. Second, to work. Second, the work done by the system. So here the energy is converted in two forms. First in work, second internal energy. Where delta Q is heat supplied to the system by the surroundings. Delta W work done by the system on the surroundings. And delta U change in internal energy of the system. Alright. Differential form for infinitesimal changes, the law is written as del Q is equal to du plus del W. So this is very important. What is del and what is d? So note here, we know internal energy is a state function. Yes or no? It means it depends on initial and final position. It does not depends on path. It is a path independent function. Whereas heat and W is a path dependent function. It depends on path. It does not depends on initial and final position. So del this del is used for path dependent functions. Here the path dependent functions is Q and W, while D is used for internal energy because internal energy is a state function. Its differential is exact. All right. So the difference is, I think, clear. All right. First one, internal energy, path function, state function, and work done, and in work done and heat is a path dependent function. Relationship between delta Q and delta U, heat supplied and change in internal energy. So if a system goes from initial state I to final state F, initial state I to final state F, as on figure here, PV curve for cyclic process, along the different paths, path B and path D. Alright. So in that case, delta Q and delta W will be different for each process. Here question arises why? Because heat and work both are path dependent function. It depends on path. It does not depends on initial and final position. So here the path is different. So their value will be different. All right. So this is important, very important concept. So here the path is from path B and from path D. In both paths, the amount of heat and the work done will be different. However, the quantity delta Q minus delta W is found to be the same for all paths. Why? Because the change in, or we can say the delta Q minus delta W is equal to internal energy, or internal energy is a path independent function. It depends on initial and final position. Alright. So here in both processes, uh, for path B and for path D, the change in internal energy is equal because it does not depends on, because you look at here, the from path B and from path D, the initial and final position is same now. So we can say the internal energy found to be same. This path independent quantity is the change in internal energy delta U. Alright. So we can say delta U is equal to delta Q minus delta W. Change in internal energy due to phase transition, liquid to vapor. So given mass of water 1 gram, latent heat of water 2 to 5 2256 joule per gram, volume in liquid phase VL is equal to 1 centimeter cube, volume in vapor phase 1671 centimeter cube, atmospheric pressure 1.013 into 10 raised to the power 5 Pascal, heat added delta Q. Here we will calculate by the formula mass into latent heat. So delta Q is equal to 1 gram into 2256 joule per gram. So it will be 2256 joule. Alright. Now work done delta W. So delta W is PdV, and here the change in volume is Vg minus VL. So put the values. So it will be 1.013 into 10 raised to the power 5 into Vg, 1671 into 10 raised to the power minus 6 minus 1 into 10 raised to the power minus 6. When we solving this, you will be get 1.013 into 10 raised to the power 5 into 1671 into 10 raised to the power minus 6. Alright. So further calculation, you will be get delta W work done is equal to 169.2 joule. Now change in internal energy delta U, here we will calculate using the first law of thermodynamics. So mathematically, first law of thermodynamics, delta U is equal to delta Q minus delta W. So put the values of delta Q and delta W, you will be get 2256 joule minus 169.2 joule. So solving this, you will be get 2086.8 joule. So this is the change in internal energy during phase transition, or we can say liquid to vapor. Alright. Now summary. Heat is uh, energy transferred between systems due to temperature difference measured in joules or calories. Heat is a path dependent quantity, meaning its value depends on the specific route taken between states. State functions like pressure, volume, temperature depend only on initial and final states, not the path taken. So here it does not depends on path. It depends on initial and final position. Path functions like heat and work depend on the specific processes or path taken between states. So we can say heat and work depends on path. It does not depends on initial and final position. All right. Heat transfer can occur through state change Q is equal to ml or temperature change Q is equal to mc delta T. Internal energy U is the sum of molecular kinetic and potential energies within a system. So internal energy changes can occur through heat transfer or work done by or on the system. So, or we can say it is a energy, or we can say sum of the energy due to molecular configuration and the due to molecular movement. So the energy due to the molecular motion is kinetic energy. The energy due to the molecular configuration is potential energy. So sum of kinetic energy and the potential energy is equal to internal kinetic energy. Work done W is calculated as an integral of the pressure times change in volume. It means integration P dot dV. Pressure into change in volume. This is also the formula of the work done. First law of thermodynamics states delta Q is equal to delta U plus delta W. Heat added equals to the internal energy changes plus work done. Alright. For phase transitions, the change in internal energy can be calculated using first law of thermodynamics. So it will be uh, delta U is equal to delta Q minus delta W. So this is very important concept. All right. Now practice questions. So this is homework for you. First, what is the formula for the first law of thermodynamics? So here you have to find out the a mathematical term of first law of thermodynamics. All right. Second, in a process where no heat is exchanged with the surroundings, no heat exchange means Q equal to 0. What is the this process is called? So here you have to find out the process name where the exchange of heat should be 0. Third, if a gas expands and does 200 joule of work while absorbing 500 joule of heat, what is the change in its internal energy? So here you have to find out the change in internal energy. How we can proceed? So we know first law of thermodynamics. So heat supplied is equal to change in internal energy plus work. So here work is given. All right. So using the first law of thermodynamics, it is solvable. What is the units of heat and work in the SI unit system? So here you have to find out the units of heat and work. So we know uh, heat and work both are energy. So the SI unit of heat is joule. So the SI unit of work is joule. All right. When a gas is compressed, does the work done by the gas on the surrounding have a positive or negative value? So here you have to find out the uh, sign of the work done, positive work done or negative work done. All right. So these 5 questions are homework for you. All right. Thank you for your attention.